Alright, hey guys, this is a test problem that comes up from time to time, and so I wanted to help you out with it. It's a basic application of Gauss's law, which at this point you should be pretty familiar with, so we're going to talk a little bit about how to use Gauss's law in this particular problem, because this is one of the few questions that we give you where you can't just straight up plug and chug and figure out what the answer is. You actually need to do a little bit of integration on this one. So let's try it out. So here's the situation. They give you some sort of a cylinder, they tell you it has some charge inside of it, and they're looking for the charge inside. Usually they'll give you some indication of what's going on with the E field here. So in this case, let's say that the E field is going to the right. And let's suppose that they give you a couple different values of the E field, which is a little bit strange to think about. But suppose that the E field on one side of this cylinder, all the way over here, in a place where I'll call this E0, if that's okay with you. Maybe this is 500 newtons per coulomb. And then way out here, let's say that that's at a length of 20 meters or something like that. So I'll call this E20. In this case, it might be equal to, let's say, 400 newtons per coulomb. Something like that. Okay, so that's the basic setup for this problem, and then they're asking you for the Q enclosed. So right off the bat, the fact that they're asking you for an enclosed charge, it should ring all sorts of bells for you that this is a Gauss's law problem. Remember, Gauss's law is really the only equation on the equation sheet that has anything that looks like Q enclosed on it. So that's probably a good place to start. Okay, so in this case, when we're using Gauss's law, of course we need to draw a Gaussian surface. Otherwise, we're not going to be able to integrate any of the things that Gauss's law asks us to integrate. So I'm just going to, for simplicity's sake here, get rid of these extra little arrows that I have, just to kind of smooth things out a little bit. Okay, so what is Gauss's law? So Gauss's law is that one E dot dA is equal to Q enclosed over epsilon naught. So epsilon naught, of course, is a constant. The rest of this we need to figure out. We don't know what E and dA are in this case. All right, now this brings up an interesting point here. Whenever you're dealing with these area vectors are typically going to point outward from a surface. So in this case, when we're dealing with this cylinder, we have an area vector out here on this end cap, which points in this way. So I'll call this A20, just to be in line with the notation that I was using previously. And over here I have an area vector, which if you can kind of envision this back surface sort of pointing out, this is A0, like that. Okay, great. So here's our, maybe this will make it a little bit clearer. So there are our area vectors for this problem. And in fact, we actually have a third surface, which is the surface which goes all the way around the cylinder. But in this case, we're only interested in areas where E dot dA is anything but 0. Right, so if you think about, so a dot product, right, dot products are what, sine or cosine? They're cosine. Okay, so when you have an area vector which points out from this side wall of that cylinder, that's going to make a 90-degree angle with this E vector here, right? E, even though it's decreasing as we go from one side to the other, is still always pointing to the right. So if my area vector is kind of coming out of the page at us and my E vector is to the right, E dot dA along that entire side surface is going to be 0 because the angle between them is 90. But something really interesting is going to happen with these two area vectors here. So we do have to be careful about that. Okay, so in this case then, E dot dA, so along that left surface, along that left cap that's kind of pointing away from us, what do we have? So at this point, we have E0 dotted with A0, and technically there's a cosine of 180 degrees, right? Because my E vector is pointing to the right, my A vector is pointing to the left, so the angle between them is 180 degrees, which leaves me with a negative sign on that E naught, A naught business. So there's that first bit, and then I'm going to add E20, A20. Right here, A20, that end cap on the right side, and the E vector are pointing in the same direction, an angle of 0 degrees, and a dot product lands us with just a positive 1, right? So we just end up with plus here. That equals Q enclosed over epsilon naught. And now it's actually really straightforward, because now we can figure out what these areas are, right? Numerically, they're both going to be the same magnitude. They're both going to be just pi r squared for both of those areas there. You have E naught, they gave you that value. You have E20, they gave you that value. And so now you can just solve for Q enclosed, and it's really straightforward. So the tough part here is drawing the picture and getting it so that those area vectors are pointing in the right direction, and so you know which one to look for. So that's the key to this problem. Good luck.